Hello everyone, welcome to today's live broadcast, development of a new online Micro-Viscometer for APC and UHPLC applications. I'm Ethan Castillo, the multimedia producer for LCGC, and I'll be your moderator for today's event. We're pleased to bring you this educational web seminar presented by LCGC and sponsored by Wyatt Technology. Since 1982, Wyatt Technology has been the recognized leader in light scattering instrumentation and software for the characterization of macromolecules and nanoparticles in solution. It provides cutting-edge tools for determining absolute molar mass, size, conformation, charge, and interactions using multi-angle static and dynamic light scattering, differential viscometry, field flow fractionation, electrophoretic mobility, and composition gradients. Wyatt's dedication to providing customers with comprehensive training and personal support makes it the golden standard in this field. More information can be found at www.wyatt.com. We have a few important announcements before we begin. This webcast is designed to be interactive, and we encourage you to ask questions during the event. You can submit questions by typing them in the Q&A box, which can be found on the right-hand side of your screen. You can enlarge the slide window by clicking on the small green icon in the upper right-hand corner of the slide window, or by hovering your mouse over the lower right-hand corner and dragging the window to the desired size, and the slides will automatically advance during the event. If you have any technical problems viewing or hearing this presentation, please click on the question mark help widget in the dock at the bottom of your presentation window. I would now like to introduce today's speakers. We are pleased to be joined today by Dr. Stephen Trainoff and Chris Dang. Dr. Stephen Trainoff is Wyatt Technology's Chief Scientist, responsible for developing new analytical instrument technologies. He obtained his Bachelor of Science degree from the California Institute of Technology and his PhD from the University of California at Santa Barbara, both in physics. Dr. Trainoff is a Fellow of the American Physics Society. Chris Dang graduated from the United States Naval Academy with a Bachelor of Science in Oceanography. After serving 6 years in the Navy in the submarine, meteorology, and oceanography communities, he completed his PhD studies in organic chemistry at the University of Florida. His research focused on the synthesis and characterization of hydrogels that can self-heal using dynamic covalent chemistry. Chris joined Wyatt in 2018 as an application scientist in the analytical services team. His focus is on polymer applications and characterizations. And thank you both for joining us today. Dr. Trainoff, you have the floor.
Thank you very much for that introduction. Welcome, and thank you for joining us on this conversation about a new online microviscometer for APC and UHPLC applications. This is a very exciting development because we believe it represents a major advance in the ability to measure viscometry for very narrow peaks that are characteristic of these systems. I'm going to begin today by talking about intrinsic viscosity, why you should be interested in measuring it, how to measure it, and some of the technical difficulties involved in making such a measurement, and how we've overcome them. And then we'll follow up with a series of applications. By no means all the things you can do with viscometry, but we'll talk about how you can use it to characterize polymer conformation, branching, and characterizing shear degradation that could occur inside the chromatography elution, how to quantify low molecular weight species in addition to the larger polymers. And then we'll wrap up with a discussion of measuring hydrodynamic radius from viscometry and how it compares to online dynamic light scattering. And then we'll have a summary. So historically, people measured viscometry in batch. And on the left here is an Hublot viscometer where you have a bulb that's filled with sample, and you let the sample flow through a capillary here on the bottom, and you time how long it takes to go between two scribe marks, and that's T. And then if you repeat the experiment for a pure solvent, you get T naught for the pure solvent, and T minus T naught over T naught is essentially the ratio of, or the difference of the viscosity of the sample minus the viscosity of the solvent over the viscosity of the sample. And this is called the specific viscosity, and it's equal to the relative viscosity minus 1. Now the specific viscosity, as defined, is proportional to concentration. So more traditionally, people divide out the concentration dependence by computing the intrinsic viscosity, which is the limit of the specific viscosity divided by the concentration as the concentration goes to 0. And this is a fundamental property that really characterizes the structure of polymers, the chain conformation, and the interaction with the solvent, or the thermodynamic quantity of the solvent. The specific viscosity is also directly related to the volume fraction of the polymer in solution. So if we can measure the mass by light scattering or other methods, then we can get from this the hydrodynamic radius. So in a classical measurement of a batch intrinsic viscosity, typically what you have to do is prepare a series of samples and measure the specific viscosity divided by concentration for each sample at different concentrations. So here on the bottom axis we have the prepared concentration. On the vertical axis we have the specific viscosity divided by concentration. And then you fit this to a line and you extrapolate to low concentration. Now when you use this in the context of chromatography elution, the process of fractionating means that you're almost always in this limit of very dilute solution. So we're going to use as a proxy for the limit of the specific viscosity divided by concentration, limiting to 0, we're just going to use the ratio, specific over concentration. Now, it's a great simplification when you use it as an online detector as opposed to a batch detector. Okay, now there's many applications for online viscometry. One of the earliest ones was to try to determine molar mass distributions by using a process known as universal calibration. This requires that you know a lot about your sample ahead of time, in particular the Markowink coefficients, which we'll talk about in a second. And it's really gone out of favor because if there are interactions on the column or some sample that's degraded, then what comes out of the column isn't necessarily representative of what went into the column. And if you're using a calibration method, you're converting the time to go through the column into an effective molar mass. And in fact, with light scattering, you measure the molar mass directly, independent of the time that it goes through the column. So in more modern time, you can use the intrinsic viscosity as an online detector to literally look at branching and conformation in a Markowink-Sakurada analysis, where we're going to measure the intrinsic viscosity from the viscometer, and we're going to compare it to the mass as measured from the light scattering. And when you combine all these detectors, you can extract from that the hydrodynamic radius, RH, and you can also extract the root mean squared radius if you have a model for the shape of the polymer, such as a random coil. Now, the Markowink-Sakurada analysis is a very time-honored way of characterizing polymers, and typically one gets a logarithmic, a straight line on the log-log plot, and the slope of that line tells you information about the conformation of the polymer and its interactions with the solvent. So a linear molecule in a thermodynamically good solvent has a slope of about 0.7. In a poor solvent, it's about 0.5. So just by looking at the slope of such a plot, you can determine whether or not it's in a good or bad solvent. Oligomers are typically around 0.5 because they look, they're quite small. In spheres, because they have effectively the same density for all sizes, it's independent of the intrinsic viscosity is independent of the sphere radius, so you get a slope of 0. And similarly with large chains, you can get a ratio of 0.8 to 1. And in general, the Markowink-Sakurada exponent decreases as you add more branching. So this is a way of asking, for example, if you go from linear to branched, how much branching there is, you can actually extrapolate or measure the number of chains per mass and estimate their length. So linear polymers typically have linear Markowink-Sakurada plots, and curved polymers indicate the presence of branching. Okay, so let's talk about how we do this in an online context instead of a batch measurement. Well, the very simplest online viscometer is simply a capillary. So here's a capillary similar to what we had in the Ubalo viscometer. You take your solvent and you pump it through the system, and you measure the pressure drop across this capillary with a pressure transducer. You then inject a sample and you watch the pressure drop increase, and from that you can get the specific viscosity or the relative viscosity. But there's a problem with using simple capillaries in online viscometer. The first is that regardless of how good your pump is, it's not going to be perfectly noise-free. And so a very good modern chromatography pump has a pressure pulse of around maybe 0.1%, and those pulses tend to look like peaks. So here I have an example of a measurement of a protein, BSA, and on the bottom axis I have the elution volume from 8 to 10 milliliters. On the right axis I have the differential refractive index, which is measuring the concentration, and we have a beautiful, and that's in this red curve, and you get a beautiful measure of the chromatography elution. And the single capillary viscometer on the left here, you can see it varies. In this case, this is in PSI from 7.110 to 7.115, but there's lots of these pump pulses, and this is limited by the pump. Okay, so you get a signal, but it's not a very sensitive signal, and it's really limited to about 1 part in 1,000. And that's not bad, but for the typical concentrations that come out of chromatography elutions, this means that you miss most of the interesting peaks. Okay, you can do better. And a more modern way is to use a capillary viscometer, which is for a bridge configuration. So in this case, we have 4 capillaries. Here's 1, 2, 3, and 4. And now we introduce the sample through the top of the bridge. It splits and goes through the 2 arms. So we have a left arm of the bridge and a right arm of the bridge. We have a differential pressure transducer that looks across the bridge, and we have an inlet pressure transducer that looks from the top to the bottom of the bridge. And the nice thing about the bridge geometry is if there's pump pulses, the pump pulses on the left side of the bridge should be the same as the pump pulses on the right side of the bridge. So if you're running pure solvent or pure sample through here, then DP should read 0. And IP will effectively is measuring this as if this is a single capillary viscometer. So IP will still see the pump pulses, but DP should not. And you can show with a little algebra that the specific viscosity is related to the differential pressure and the inlet pressure through this relationship. 4 times dP over IP minus 2 dP. So it's essentially the ratio of dP over IP. And like I said, the big benefit from this is that the DP transducer should cancel the pressure pulses and make it much less sensitive to how stable the pump is. It's not perfect, but it does a great improvement. Now, of course, to measure this, if I've drawn it here, if I had the solvent in all 4 arms, I'd get dP equals 0. If I had sample in all 4 arms, I'd get dP equals 0. So what we do is we add a delay volume in one arm, and this delay volume has been filled with the solvent before the measurement is made. So the sample goes in, it's delayed, and solvent comes out. So on the bottom of the bridge, you have solvent on this arm, you have sample on this arm, and now there's a bridge imbalance that you can use to determine the specific viscosity. There is a downside, namely you do have to wait for the sample to go all the way out of the delay volume before you can make another injection, because this thing has to be pre-filled with solvent. Okay, so let's talk about how well it works. So here is a graph of a modest chromatography pump, not certainly a bad one. And here is the time or volume on the horizontal axis. The inlet pressure for this measurement was between 6.965 to 6.980 psi, so around 7 psi. And the DP signal is much smaller. It runs from minus 0.0005 psi to 0. Okay, so now if we take the ratio or measure the amplitude of the noise on the IP, so here's the IP noise amplitude, and here is the DP noise amplitude, and take the ratio of the IP noise amplitude to the DP noise amplitude, you can ask how well does this suppress the pump pulses. If DP were equal to 0, then the suppression ratio would be very large. So we want the suppression ratio as big as possible. And for this case, if you just run the numbers, you find that the suppression ratio is around 25:1, which means the bridge is really helping. It's suppressing the pump pulses by a factor of 25. And that pushes our previous sensitivity limit from about 1 part in 1,000 to about 30 parts per million, or 3 times 10 to the minus 5. And that's a huge improvement. And so that allows you to use this as an online detector very effectively. Okay, so the question is, why is it that we only suppress the pump pulses by a factor of 25:1? After all, the whole point of the bridge is that the pump pulses as seen by the left arm should be the same as the pump pulses as seen by the right arm, and that would give a complete cancellation of the pulses as seen by the DP transducer. But in fact, that's not the case. And why? So we did a little bit of research and we discovered that, in fact, although you think of solvents as being incompressible, the delay volume has a fairly large volume compared to, it's much larger than anything else in the system. So a very tiny compressibility times a large volume means that there's a net compressibility of this that's not balanced by something on the other side. So the pump pulses as seen by the left arm are a little bit out of sync with the pump pulses as seen by the right arm, and you don't get perfect cancellation. Well, now that we understand the source of the limitation of why we're only getting 25-to-1 suppression, we can do something about it. And what we did is we added an equivalent compensation volume on the other arm of the viscometer, and it's placed in such a way that it's in series with the pressure transducer so that the sample never flows through this arm at all. The sample goes through these capillaries and these capillaries, but the compensation volume is just there to balance the compressibility. And when you do that, a very remarkable thing happens. So here is a plot. On the horizontal axis is the volume that we put in the compensation volume. And remember I said it's 25-to-1 when there's no compensation volume in here. So on this axis I'm starting at 10. So at 0, way here very far to the left, it would drop, the suppression ratio would drop to 25, which is way down here. But as you change the volume, you see that there's a resonance. As soon as you get the compensation volume compressibility matching the delay volume compressibility, all of a sudden your suppression ratio jumps to well over 200. So now, instead of being limited to only 25-to-1, we can do 200 or even higher. And that means that the basic sensitivity jumps by another order of magnitude. And so now we can measure down to a sensitivity of around 3 parts per million. And so this is an idea that's very simple but incredibly powerful. And it's also one of the patented innovations in this device. Okay, well now we have an instrument that's incredibly sensitive and it's very immune to the pump pulses. Not completely immune, but has tremendous suppression of the pump pulses. And these bridges work beautifully, but one of the key points of bridges is that you have to get all 4 of these capillaries very well matched. And however well you match them, as you use the instrument over time, and let's say you played a little bit of sample on the inside of the capillaries, then this bridge will slowly get out of balance. When it's perfectly balanced, dP will equal 0. When it gets slightly out of balance, then you'll lose sensitivity and you'll lose range. So the problem with bridges, which is well known, is they work great until they get out of balance. And here's a classic example of a bridge that gets out of balance. Now, the viscometer is not going to fall apart like the Tacoma Narrows bridge, but it's still not good. We added one more innovation, which is the ability to automatically balance. This is another patented innovation in this product. And the historical way of balancing a bridge is to measure how far out of balance it is and then adjust the length of one of these capillaries to bring dP equals 0. And so that's fine. You can cut and file and adjust lengths, or you can try using little slidings of bellows systems or sliding O-rings, but those are very problematic and not very reliable. And we realize it's a very simple solid-state way of doing this accurately, and that is to avoid cutting. And the way to do it is by temperature regulating one arm of the bridge independently of the temperature of the other 3 arms of the bridge. Now, we didn't talk so much about the temperature sensitivity of viscometry, but the viscosity of a solvent varies by roughly 2% per degree. So if you're trying to measure down to parts per million, you have to keep the temperature stable to parts per thousand. So we regulate these and keep them stable to parts per thousand, but then we keep the temperature of this one also stable to parts per thousand, but at a different set point. And by adjusting this set point relative to these 3, we can automatically balance the bridge at any time by just pushing a button. And the nice thing about putting the thermal adjustment in this arm is this, during the run, only sees pure solvent coming through here. So the sample does eventually go through here after the run is over, but during the run, you only have pure solvent. So if you increase the temperature of this arm by 1 degree relative to this, it reduces the viscosity of the solvent in this arm by 2%, and therefore it's the same as making this capillary effectively 2% shorter. So by adjusting temperature, you can effectively change its length, or the pressure drop in it. And so here's how it works. So here on the left axis, I have the dP transducer, and it should be 0. And you can see in the black trace, it's actually minus 0.017 or so. On the right axis, we have the temperature of that compensation volume, of the thermal tuning arm. And so it originally starts out at 25 degrees C. And in order to balance the bridge, the first thing we do is we check the 0 by putting it into purge mode. So now we know what the 0 is. And then we slowly ramp the temperature of the tuning capillary up. And sure enough, the bridge pressure follows it. And when it reaches 0, we restabilize the temperature and hold it very steady. and now we have the bridge balanced. This is very simple, very effective, just takes a couple minutes, and you can do it anytime. And that means that now you have something that's very immune to pump pulses that's essentially always balanced. Okay. Okay, so let's put this all together and see what this looks like in terms of a real instrument. So here we have the plumbing diagram for the ViscoStar, and the first thing that you do is you introduce the sample from the top. We have a system pressure sensor that checks to make certain that the pressure of the system has not gone too high, and if it does, it protects the system by opening up a bypass valve. So if you ever get a plug, or if you inject some sample that's a very high viscosity, the system will automatically protect itself. Next, the sample runs through a heat exchanger that ensures that it is at the measurement temperature, and then it splits into the two arms of the viscometer. So we have on the left arm R1 and on the right arm R2, and it's a 50-50 split. The sample then goes through the delay volumes on the left, and the solvent comes out in this arm. This is where our tuning is done. And then the sample goes through the R4, and that gives us the difference pressure that's recorded by the DP, which measures across the bridge, and the inlet pressure, which is measured top to bottom of the bridge. Then the sample gets recombined, and then it exits the instrument. The compensation that I was talking about is here in this arm, and this allows us to do the pulse correction that gives us our extremely high sensitivity. Okay, so that's what it looks like in a schematic. Here we're going to show you the hardware. So here the inlet is at the front of the instrument is to the left. The sample enters through a counterflow heat exchanger, and that makes certain that the outgoing fluid transfers its heat to the incoming fluid, so that the fluid that comes into the bench is essentially at the right temperature that we want to make the measurement. The spool here has all of the measurement capillaries wound over a copper bridge, and it's temperature regulated with a Peltier, so we can control that very accurately. And since it's wound on a copper block and potted, we have very good thermal matching of all of the arms of the bridge to each other. Here are the delay columns, and you can change the number of delay columns in order to adjust the delay. The thermal tuning is a spool here, and so this is regulated to a slightly different temperature to that one. And it's the difference in temperature between the two that allows us to automatically balance. And the two transducers are here. So this is the DP transducer that looks across the bridge. This is the IP transducer that looks top to bottom of the bridge. And the DP transducer is really the critical one, and it's a good thermal contact with the actual bridge. And finally, we have the compensation, and this is just a volume of fluid that's matches the compressibility of the columns. And last, we temperature regulate the overall bench. Here's the measurement temperature regulation for controlling the bridge very precisely. And then we have a large Peltier, air-cooled Peltier system that will raise the entire bridge from 0 to 70 degrees C to accommodate the wide temperature range. And by regulating both the front and the back of the bridge, we keep the uniformity of the temperature in the bridge very precisely controlled. And so that works very well. But this talk was about how we can make measurements of very UPLC and APC systems. And so let's talk a little bit about the challenges that are associated with making measurements of this new generation of chromatography. So first, let me concentrate on the right, which is an elution of 200K and 30K polystyrene mixture that's been fractionated. So here's the 200K peak, here's the 30K peak, and this is done with standard chromatography. Now, the width of this 200K peak, this is quite typical for a narrow standard. It's around 300 microliters wide in volume. And in order to make a good measurement in the viscometer, we want to make certain that the volume inside the measurement capillaries is small compared to the peak, so that we introduce very little smearing as the sample goes through the system. Now, for standard chromatography, when the peaks are 300 microliters wide, that means that we could have an internal volume of, say, 30 microliters, which is 10% or so, and still get very good results. When you look at the left, which is the same 200K and 30K polystyrene sample, it's been fractionated on an APC system, then you can see a big difference. The first is the chromatography takes much less time. It comes out in 4 or 5 minutes, but the peaks are also much narrower. So this is a 72 microliter peak, and also the typical injection volumes are much smaller, so the total mass in this peak is quite a bit lower. So the fundamental challenge in making an APC or a UPLC measurement with viscometer is you need to use much smaller measurement volumes, and because the peaks are coming out very fast, you have to use much shorter time constants in your transducers and your electronics. And lastly, although I haven't talked about this, is the operating pressure within a UPLC or UHPLC or APC system is typically much higher. So typically, several hundred psi on the analysis instruments. And so you need to meet all of these requirements in order to make a system that measures well for both. Okay. So that brings us to the Micro-Viscometer. And so what we've done is we've optimized the basic technology that I've described with a bridge that only has 7.6 microliters per arm. And this is small compared to the peak width of 72 microliters, and that means that we can accommodate any small variations in the peak width in the analysis. So here I'm showing you that 200K polystyrene peak from the previous view graph blown up, but now I've overlaid the light scattering, the refractive index, and the differential transducer, and you can see there's very tiny little broadening between them. Between the viscometer and the RI, which are the sequences light scattering, viscometer, RI, we're only seeing about 5 microliters effective mixing volume. And for the entire stack, from light scattering, viscometer, and RI, we're only seeing about 12 microliters. And so this is without any corrections. This is the raw data. And so that means that we have a system that really gives very good sensitivity because it has very little dispersion. So here's an example of how well it works. So here's that same 200K and 30K polystyrene, but zoomed in a little bit more. So here's our 200K peak, here's our 30K peak. And the first thing you'll notice is that because of the APC system is very solvent efficient, that the total run was over in about 6 minutes. Now we had to take 15 minutes for the delay volume to re-empty, but look at the quality of the data. The 200K is incredibly flat in its intrinsic viscosity, and that's because the 200K is a very narrow polystyrene standard. Interestingly enough, the 30K has a little bit of a slope to it, and it's well known that the 30K is not nearly as uniform as the 200K, but because the system's so stable, we can also get good data for this tiny little peak here, which is the dimer of the 200K, and you can see it's even baseline resolved. So now we have the ability to get beautiful intrinsic viscosity measurements for not only standard chromatography, but APC and UHPLC. And with that, I'm going to hand the conversation over to Dr. Chris Deng, who's going to go into more detail about some of the interesting polymer physics and polymer science that you can do with this instrument. So thank you very much, and here is Chris.
Thank you, Dr. Trainoff. So we've designed this viscometer to be used with UHPLC. So some of you might be wondering, why would we want to use UHPLC versus HPLC? And there are several advantages. We have to consider that with UHPLC, it not only includes the autosampler, the pump, the internals, but also the columns that are designed to be used with the higher pressures of UHPLC. And so in these columns, you have beads that have a smaller diameter than in HPLC columns. And so this allows for comparable resolution to HPLC, but with a smaller column size. The downside is that these smaller beads produce higher back pressures, but these columns are designed to be more mechanically robust. So this, combined with a smaller column size, allows for reduced analysis time and solvent consumption. Additionally, since these columns are more robust, it also lowers the solvent switching time. So for the analyses within this webinar, we use the Waters Acuity APC system, but there are other systems available for use. Here you can see a typical UHPLC MALS viscometry setup. On the left, you have your UHPLC stack. And then from here, if the sample flows into your columns, in this case we used 4 Waters Acuity APC columns, and then the sample travels into your detectors, your UV detector if you have one, the microdon, or multi-angle light scattering detector, the Micro-Viscometer, and then the OptiLab UT-Rex, the differential refractive index detector, and all the data is collected and analyzed with our Astra software. Moving on to the actual samples, we first see an analysis of an epoxide sample. And you see the three signals coming from our three detectors: light scattering in red, refractive index in blue, and differential pressure in black. You can see the nice resolution, the nice separation of all the oligomer peaks in the epoxide. And you can also see that all the signals overlay quite nicely. So this micro-triple detection can accurately and precisely measure a macromolecule with the increased speed of UHPLC. If you look at the elution volume on the bottom, you notice that it's very low. So you can get up to 5 times faster analysis times. Now, I also said before that we're using 4 columns. So if you're using even less columns for your analysis, then the analysis time can be even lower. We've seen that we can do this analysis with faster times, but do we have to sacrifice anything as far as data quality goes? And the answer is no. Here in the top, we see intrinsic viscosity plotted versus solution volume for UHPLC on the left and HPLC on the right. And you can see that the graphs are very similar. When you actually look at the molar mass moments, the intrinsic viscosity, and the hydrodynamic radius values, you see that there's not much difference between UHPLC and the HPLC setup. And that also, the uncertainties are very low for UHPLC. So you have good agreement between the two results, but UHPLC provides a faster analysis time. In addition to your molar mass moments and your viscometry parameters, you can also do conformational analysis with the Micro-Viscometer. And in this case, we do it via the Mark-Hoeing plot. So like Dr. Trainoff had mentioned earlier, these are log-log plots of intrinsic viscosity versus molar mass. So in this plot, you can see various macromolecules, and when you take the slope of the plot, this gives your Mark-Hoeing A value. And the value will give you your conformation, which is seen in the table to the right. In addition to this, you can also derive branching information from your plot. If there's any curvature in the Mark-Hoeing plot, this is indicative of branching. So using our Astra software, we can also derive various branching information like branching ratio, number of branches per chain, and long chain branching. So we've seen that we can derive a number of useful parameters from the Micro-Viscometer and mols, but what are the downsides? So with using UHPLC, since it has a higher shear, you could see degradation of high molar mass polymers. So to investigate this, we looked at a branched polystyrene of around 72,000 grams per mole, and at the top of the table, you can see the analysis with normal HPLC. If you compare that to the UHPLC analysis at 0.5 milliliters per minute, you see that the parameters are largely unchanged. But if you increase the flow rate to 0.9 milliliters per minute, then you start to see a reduction in the molar mass and the viscometry parameters, indicating that it might be undergoing shear degradation. If you look at a higher molar mass sample, in this case a 900,000 gram per mole branched polystyrene, then you can see that even at 0.5 milliliters per minute, the sample undergoes shear degradation as you see reduction in all the parameters. And it becomes even more severe when you increase the flow rate at 0.9 milliliters per minute. So depending on the molar mass, the polymer may not be affected by the increased shear rate of the UHPLC. However, we are able to identify with our microdetection system shear degradation at higher molar masses. It's also important to remember that branched polymers are less susceptible to the shear degradation than linear samples. So you must also consider the molar mass of your linear samples for shear degradation. Next, we'll look at the capabilities of the Micro-Viscometer and the other microdetectors. And here we're looking at the quantification of low molar mass species. You can see a plot of molar mass versus solution volume of a 700 gram per mole polyester with a low DNDC value, and of hexylbenzene, which is 162 grams per mole. You see a nice strong signal indicating the sensitivity of the detectors, and you also see the very nice overlay of the triplicate chromatograms and of the molar masses versus solution volume, demonstrating the good precision of the instruments. On the right, you can see the table of the parameters, and you see that the molar masses also correlate very well with the given molar masses of the two species. So the microdetection system is able to precisely and accurately quantify even samples with very low molar masses, such as these. Here we see the repeatability of our instruments, and so we have a chromatogram of 3 signals: light scattering, refractive index, and differential pressure of a 34,000 gram per mole polycarbonate. And these are done with 8 injections. So this is an overlay of 8 injections. And you see that they all overlay very nicely, showcasing our repeatability. And when you look at the data table to the right, you can see that the percent standard deviation is very low. You'll also notice that there are 2 hydrodynamic radius values. The first one with a subscript of V comes from the viscometer, and the second one with a subscript of Q comes from QUELS, or online dynamic light scattering. And so you can see the values from the viscometer are much more accurate and more precise, since the viscometer is a much more sensitive instrument in determining hydrodynamic radius than dynamic light scattering. And in this slide, we see the same thing, but with a lower molar mass sample, a 760 gram per mole polystyrene. And once again, you can see the very nice overlay of the 8 injections. And also you can see here the increased sensitivity of the ViscoStar in quantifying hydrodynamic radius. In this case, we can quantify it to less than 1 nanometer. And when compared to DLS, you can see the increased sensitivity even more clearly. The DLS value is definitely wrong. You're obviously not going to get a hydrodynamic radius of 3.4 nanometers for a 760 gram per mole sample. So we'll look at how the MicroViscometer can actually help you in your day-to-day operations. We've seen that the MicroViscometer, in conjunction with the MALS detectors, can produce a number of parameters, including intrinsic viscosity, hydrodynamic radius, your conformation and branching information, with good precision, accuracy, repeatability, and sensitivity. But since it's able to be used with the UHPLC, you also reduce the analysis time and the solvent consumption. So let's take a look at that second part, the solvent consumption. Let's say you're using hexafluoroisopropanol, HFib, which costs $1,000 per liter. And looking at a hypothetical workflow, let's say you have a flow rate of 1 ml per minute, and your experiment takes 30 minutes, and you're doing 10 experiments per day. And you're doing experiments 300 days out of the year. You're taking it easy. So you multiply this volume times $1 per milliliter, and you get a solvent cost of $90,000 annually. If you use UHPLC, you would use 1/3 of the solvent you would for HPLC. So your solvent costs will only be $30,000. So that's an annual savings to $60,000. And this is just a hypothetical example. Your workflow could be even more rigorous, and you could save even more money, allowing you to buy even more wide detectors. We certainly wouldn't mind. So suffice to say that using these UHPLC compatible detectors could greatly reduce your operating costs. So how else can the MicroViscometer help you? We can look at a real-world example. And in this case, the MicroViscometer could be used for process monitoring and QC of polymers. So an example that you all may be familiar with is the process monitoring of polyethylene terephthalate, or PET. In this case, intrinsic viscosity is quantified because it gives an easy measure of the mechanical properties of the polymer. So it can identify potential weakening of the polymer. In the case of PET, it can absorb moisture, which causes chain scission. So this can be seen in a reduction in intrinsic viscosity. It's also very useful because you can do it quite easily at various stages of polymer processing. You can do it when you receive the batch polymer from a supplier. You can do it after you do melt processing. You can do it after you process it into whatever component that you're making. The MicroViscometer enhances this analysis by reducing the amount of time required for doing the quantification. For typical milk capillary viscometers, I believe they say the analysis time is around 20 minutes, so the MicroViscometer can do it even faster. And you also use less sample and less solvent, reducing your operating costs. So in summary, we're able to design this viscometer with very low dispersion and being able to withstand very high pressures. So it's really the first viscometer that's compatible for use with UHPLC. And the viscometer combined with the other microdetectors can produce a vast array of macromolecular parameters that are useful for analysis. And it can do so with excellent sensitivity, repeatability, accuracy, and precision. And since all these detectors can be used with the UHPLC, you get reduced analysis times and reduced solvent consumption, which translates into higher throughput and reduced operating costs. And with that, this concludes my presentation. If you're curious about any of the topics that were discussed in the webinar, such as moles or viscometry or polymer analysis, feel free to click on the links below, and I'll be happy to take any questions that you may have. Thank you very much.
Well, thank you both for such informative presentations. Before we get started on the question and answer session, I'd like to remind our audience how to submit questions. You can submit questions by typing them in the Q&A box, which can be found on the right-hand side of the presentation window. And we'll try to answer as many questions as we can. Here's our first question. What applications are used for proteins and antibodies?
So I'll field that one. So in the presentation, we focused mostly on polymers because that's the majority of viscometry applications. But we also have beautiful data for proteins and antibodies, and both in standard chromatography and with UHPLC. So it's a fine application for both, and it's a very good way of measuring the hydrodynamic volume or hydrodynamic radius for things that are too small to easily resolve with dynamic light scattering.
Excellent. Here's another question. Is the MicroViscometer able to handle aggressive solvents like HFIP on a continuous basis?
Chris, do you want to field that one?
Sure, yeah, I can handle that. So the MicroViscometer is composed of very robust materials, stainless steel and whatnot. So it can withstand such aggressive solvents such as HFIP for prolonged operation.
Excellent. Another question just came in. Does this detector work for aqueous polymers or polysaccharide?
Yeah, so that goes to the previous question we were discussing earlier. Yeah, so there's a very good body of literature for using online viscometry for aqueous polymers, such as polysaccharides, so it's a very good application. It's very much equivalent to the polymer applications we were showing, but in aqueous solvents. And yes, it works very well for that.
Here's another question that just came in. Have you sped up the runtime for the IV with better quality of results?
Yeah, I think I'll also take that one. So as I mentioned earlier, the benefit and the disadvantage of the delay volume is delay volume allows you to get this beautiful operation and beautiful sensitivity, but you do have to wait for it to empty out before you make another injection. And so with this instrument, the runs that I was showing at the very beginning, the elutions were coming out in about 6 minutes or so, and then we had to wait another 6 or 7 minutes for the delay volume to empty. So the total runtime was about 15 minutes. And this is compared to, that was with the APC application. And this was compared to the standard chromatography where the runtimes are around an hour. So it's much faster than the standard chromatography. So you still get the benefits of using the APC speed.
Another question. Is Astra software running the Waters APC when in use with Microdon and the Waters DRI?
Yeah, I can field this one. So we're using the Waters Empower software to run the Waters APC, whether it's running with their RI or our own refractive index instrument.
Yeah, and I'll add to that is we can run with either configuration. So if you already have the Waters RI, you can use it, and otherwise you can use a Wyatt RI. So we can use essentially any RI detector that has the requisite low dispersion, which is key.
Thank you. Here's another. Can the Micro-Dawn Micro-Viscometer Micro-RI detector set be used with standard GPC?
Yeah, I think I'll take that one too. So the answer is yes. The difference between the Micro-Viscometer and the ViscoStar, the standard ViscoStar 3, is the Micro-Viscometer, because it's typically used with lower flow rates, has a slightly higher shear. And so you can still use it, the Micro-Viscometer, for large branched polymers that are not appropriate for APC. But you may run into problems with the fact that it applies a higher shear. So there's a role for both the ViscoStar 3 for standard chromatography and the Micro-Viscometer for chromatography. But if you have the Micro-Viscostar, you can still use it. Just have to be concerned that you're applying a slightly higher shear in the measurement.
Excellent. Another question for you. How does the sensitivity of the Micro-Viscometer compare with the standard viscometer?
Yeah, so I didn't talk so much about that, but in fact, for the same injected concentration, the signal on the Micro-Viscometer is actually 2 times higher, so it's twice as sensitive as the standard ViscoStar. And that's, again, a consequence of the higher shear that gives you higher signals. The noise is effectively the same, but the signal being a factor of 2 bigger gives you better sensitivity for the low concentration peaks. And when I showed the comparison between the standard chromatography and the APC chromatography, you saw that the injection volumes are typically quite a bit smaller, and therefore the total peak areas are smaller. And so having the additional sensitivity really helps preserve the performance even when you're injecting much less samples.
Are the delay columns matched to APC columns volume?
Yeah, so one of the things when configuring the instrument is you have to make certain that the delay columns inside the viscometer are matched to the time for the peaks to come out. Now, with the APC systems, we're typically just put one delay column in, and that adjusts so that the peaks come out in, say, 5 minutes or 6 minutes, and then the delay column empties out in 6 minutes. If you're using fewer analytical columns, you can reduce the size of the delay and speed up the overall runtime. But yes, they are matched to the chromatography columns.
Thank you. Another question. What are the overall range and sensitivity limitations of the UHPLC microdetector systems?
Yeah, so I can take that one. So if you're using UHPLC, there's typically a upper molar mass limit of around 2 million. And for the lower range, we can see about 100 grams per mole. If we're talking about quantifying hydrodynamic radius, then we can measure down to below 1 nanometers.
Thank you. Here's another question. Is mols preferable over LALs detectors for molar mass determination?
Sure. So there, with MALS is an acronym for multi-angle light scattering, and the idea is with several detector angles, you can get the variation of the scattering as a function of angle, and that's a measure of the RG, or the radius of gyration of the molecule. If you have only one angle, such as only right angle or only low angle, which is the RALs and LALs applications, if you have only one angle, you lose the ability to measure size. If you have two, say right angle and low angle, you can get a size measurement. The problem is if you have some dust particles or some particles that shed off the column, that noise primarily shows up in the low angle detectors. So if you only have a low angle detector, that's the one that's most contaminated by the dirt. So by having a range of angles, the multi-angles, you can not only get the angular variation, but you can also get good suppression of the dust and therefore get accurate measurements of size. So yes, having multi-angles is a huge benefit over having just one or two angles.
Here's another question. Does your software support universal calibration?
Yes, it does. We haven't talked a little bit about universal calibration, but in the early days of chromatography, calibration methods were the basically the only way to use it, where you correlated the elution time through the column to a molar mass, or you could do, and that's standard calibration, or you could do universal calibration where you use both the viscometry and the elution time to get molar mass. And you can still use the instruments that way, but it's still going to be susceptible to interactions on the column, so things that get anchored or they get absorbed to the column and then emitted late will give you an inaccurate result. The nice thing about light scattering is, since we don't care about when the sample comes out, we measure the molar mass of the eluent directly, then we don't have to worry about column interactions. And in fact, you can then determine whether or not you have column interactions or issues with chromatography by comparing the size molar mass you would get from universal calibration to that you get from light scattering. Similarly, historically, people would use the Mark-Howing plots, which relate the intrinsic viscosity to molar mass. And if you knew the material and you knew the Mark-Howing coefficients, then you could use the measured intrinsic viscosity to get a molar mass. But when you have the entire detector system, you can measure the Mark-Howing plot directly rather than having to try to infer the molar mass from a known value.
Here's another question. Do you recommend using the Micro-Viscometer alone for QC and process monitoring applications instead of including light scattering?
Yeah, I'll take that. We're not specifically recommending that we use the Micro-Viscometer alone, but it can be advantageous in that it's not as sensitive to things like contaminants such as dust or other large particles, such as light scattering is. So it could be used for QC of samples that may be a little more dirty, or if you don't want to take the time to process or clean the samples.
Yeah, but let me also add that in general, the more detectors you have, the better view you get of the sample. Each detector adds a new dimension. Of course, for a process control or quality control, you don't want to get necessarily a too detailed view, because you want to have a release criterion or a clean measurement. And the robustness of the viscometer, because it doesn't see the particles, makes it ideal for that.
Another question just came in. You have your detectors in series. Traditionally, there is a split flow between the RI and the viscometer. Have you tried this configuration, or is it not necessary?
Yeah, so this is a great question. So people have used both series detection and parallel detection. The advantage of parallel detection is you get, in theory, you can get less broadening. The downside is it's very difficult to maintain the split ratio without having a mass flow controller. So our experience has been that series detection is always much more robust, and as we tried to demonstrate in the webinar, that the dispersion that you get is very low with the system. So the benefit that you might get by having a parallel detection would be very modest, and then the downside, of course, is if the split ratio is not very well controlled, you actually introduce shifts in the detectors between the shifts in the arrival of the peaks between the various detectors. So we don't recommend parallel detection.
Thank you very much. And one more question for you. Can we use the ViscoStar without LC separation, so direct injection of amyloid to detector to determine RH?
Yeah, so the whole webinar was focused on using it as an online detector where you fractionate the samples. You can use it in so-called flow injection mode, where you inject a small pulse, and that works fine. The idea there is you're not going to fractionate the sample, so you'll get an average of the species, or of the RHs or the molecular weight, what comes through. This is the advantages. It's very fast. The disadvantage is you don't get the full size and molecular weight distribution that you get from doing chromatography. But yes, using a flow injection mode works just fine, and it's very fast.
Well, thank you both very much. Unfortunately, we are out of time. I'd like to thank the audience for attending and participating in today's event. I'd also like to thank our sponsor, Wyatt Technology, for making today's educational webcast possible. Today's webcast will be available for on-demand viewing through June of 2019. You'll receive an email from LCGC alerting you when this webcast is available for replay. We invite you to forward that announcement to your colleagues who may have missed today's live event. Thanks to all for joining, and we'll see you next time. Goodbye.